Muchas gracias a los organizadores de la conferencia. Es mi primera vez en Argentina y en Ekoparty, y ya muy bueno. Lo siento. That's all I got. Hi, I'm Maddie Stone, and this talk is all about a Samsung in the wild exploit chain. So, as I said, that's my name, that's me. I am a security researcher at Google Project Zero, and we are a team of offensive security researchers. So the majority of our team is focused on vulnerability research, exploit dev, to show what are attackers likely doing, to find the same bugs, etc. But my role is focusing instead, first off, on the zero-day exploits that are actively exploited in the wild. So the ones that the attackers are actually using, not the ones that they could hypothetically be using. And as a refresher, a zero-day vulnerability or a zero-day exploit are those vulnerabilities that defenders don't yet know about. So there's not the patches available for them. We don't realize there's a hole there that could be exploited. Only those attackers know about the hole. So that's what I focus on a day-to-day basis. And so my whole role and my job and goal is we learn from all of these zero days that are discovered in the wild, that are detected, and make sure that we learn as much as possible from them in order to make it harder for the attackers to come back, write another zero day, and use it against folks. So that's what this talk is about. Specifically, it's about a sample that was found in the wild, which targeted Samsung devices and involved 0 days. So this sample was obtained by the Google Threat Analysis Group, and they attributed this sample to a surveillance vendor, a commercial surveillance vendor. So this sample in particular was a native library for an Android app, and it involved 3 different zero-day vulnerabilities that were 0-day at the time of the discovery of the sample. This sample was discovered during a testing phase or during a testing practice, so we were not able to see or study the whole chain from start to finish. This sample is also from late 2020, so that's an important thing to keep in mind when we sort of evaluate the state of the art, what was vulnerable, what was not, etc. So let's walk through what we're going to cover in this sample. There is not the initial attack vector included in this sample. So the sample is a native library that would run within an Android application. So that means that the initial attack vector could have been some vulnerability in a common app where they knew they could then load this library to run. Or it could have been something like campaigns we saw earlier this year, where attackers were able to have apps installed on their targets' phones. But either way, we know that we're starting in sort of the least privileged app context, which is called untrusted app. So that's where our exploit we're analyzing starts from. So the first thing it does once it's running and loaded in this untrusted app context is it's going to use a vulnerability to get arbitrary file system read or write. Then it's going to figure out how to load its next stage in a more privileged than untrusted app, more privileged context, a system app. Then we're going to use another vulnerability to leak information from the kernel. Finally, we have a privilege escalation through the display processing unit driver. And woo, then we're going to talk about how it got root from there. So we have a lot to cover in 15 minutes. All 3 of these vulnerabilities were patched in March 2021 in the Samsung March 2021 release. So the devices that were targeted with this chain were specifically Samsung Exynos devices. So if you're not aware, Samsung devices sort of run on 2 different CPUs. Devices sold predominantly in the United States and China, as along with a handful of other countries, run Qualcomm CPUs, whereas the rest of the world largely runs on the Samsung in-house developed chip, the Exynos. Specifically, this chain could only target those Exynos devices because vulnerability 2 is triggered using the GPU driver that is specific to the Exynos chips, and vulnerability 3 is specifically in the driver that only runs on these Exynos. And lastly, it targeted phones running kernel versions 4.14. And so in late 2020, when these were 0-day and the sample was found, this would have included phones like the mid-tier A50, A51, along with the flagship S10. So why did I think this was interesting enough to share about this sample? First off, I think anything in the wild is generally pretty interesting. There aren't a huge number of those samples that we get to discover and get a ground truth of what are attackers actually doing versus what do we think attackers are doing. So that first off. But secondly, all 3 of these vulnerabilities are in manufacturer-specific components. As Android vulnerability researchers, this is talked about, but it doesn't tend to be the focus of a lot of vulnerability research who are publishing blog posts generally, just because then your exploit will be specific to the manufacturer. So instead, the upstream Linux kernel, the AOSP, is what tends to get a lot of the looks and research done. So that's interesting here. And also, as you'll see, our first vulnerability we're going to cover is sort of the foundation of this whole exploit chain, and it's in a Java component, which is interesting because as vulnerability researchers, we're usually focused on memory corruption bugs, which will exist in compiled code. So let's jump into it. Here is our first vulnerability. As I said, it was patched in March 2021, and it is an arbitrary file system read and write via a clipboard. So this yellow box, the one in the bottom left, is the one that we are starting in. So we're running in our untrusted app context. And before we jump into this, we need to understand a little bit about what are content providers in Android. So they are a component that basically allows for the storage and system-wide access of data. Because Android has sandboxes that tries to separate data from each other. So the content providers is what says, let's one app contact or see your contacts, because that's stored in a separate contacts provider. And so this data is stored in sort of like SQLite tables. And a key aspect of it is that according to spec, content providers are required to implement these 6 abstract methods. The first 5, all of them except onCreate, are called by a client who wants access to the data. The other key thing to note about content providers is that by default, all applications can read from or write to your content provider, even if the underlying data is private. So when you create a content provider, if you do not go through the necessary steps for access control and permissions, it is going to be device accessible across the board. Usually, these permissions will be set via the app's manifest file, where they can set you need this permission to read or write, etc. But this is where our bug comes in. Our content provider doesn't actually exist inside of an app. It's running within the server, or the system server, which is a jar file. So it's required to do all of its own access control. One more foundational step before we can really get into it is Android file permissions. So Android uses a combination of Linux file permissions, read, write, execute, along with SE Linux. And so the system user on Android devices is the most privileged user on the device besides root. And the system server SE Linux context is very privileged because it manages a whole bunch of services critical to your device. Think of connecting to Wi-Fi, location stuff. So it has to be privileged to do all of that. And so one thing to keep in mind as we're talking about a lot of access stuff throughout this presentation is that to have access to something, a component needs both the requisite Linux file permissions as well as be in an accessible SE Linux context. So in our case, this Clipboard provider, which is a custom edition by Samsung, runs within this privileged system server. So here are some of the variables associated with it. We have the database name, clipboard image, the table name, the URL to access the content provider, and then the table. And the key part of this that sets us up for this arbitrary file system read and write is the name of this column here, _data. Because _data is a special sort of nomenclature and means something specific in these Android content providers. It allows direct access to files on the file system. So if you have a path in a column named _data, then you can use this helper function, openFileHelper, to directly open it without having to work with all of these underlying operating system internals. So this is the insert method within the Samsung Clipboard provider. And what I would like you to note is there is insert, and then the function just runs. It just runs insert. There is no access checking before that first insert call. And because this is not an app and doesn't have a manifest, that means there's no access checking at all, because it would require some sort of vetting at the beginning of this function for there to be any. So this is how you trigger the vulnerability. So what our exploit did, or not my exploit, the exploit analysis, I'm probably going to mess that up and say that a lot. It's going to get me in trouble here, is first we need to create the content values. And so this is just, the Java object that's going to say, hey, I want to put this value associated with this column or key. So in this case, there is the column, the _data special one, and then this file path, data system users, 0, new file bin. Then we have the URI to this special clipboard provider, and then we call insert. So we are adding this new value to the table, saying this custom file path goes in as data, and then we receive back a URI that points directly to that row. That new URI is the only thing that needs to be passed to open file descriptor with whatever mode you want to run in to then receive back a parcel file descriptor, which is a Java object for whatever path you put in there. And finally, then, parcel file descriptor defines a function or method called getFD, so you can get back the raw file descriptor. So pretty straightforward using that _data column. But how do they use this? So they ultimately use this vulnerability 4 times throughout this exploit. The first time here was to drop the stage 2 exploit. And so we drop it at this path. The dropped elf at that path will now have a SE Linux context of user system data file. So the key here is that apps do not have access to create or open those files, but system server did. So the exploit proxied that create and open functionality through the privileged system server process, got back a raw file descriptor, and then they were able to read and write to that file. So how was this bug fixed? Basically just adding an access check. They added this check at the very beginning of the function that says what UID is calling me, and they verified that anything that is calling this function is also already running as system. So we now have our stage 2 elf on the file system, but how do we load it? We're still running in this unprivileged context, but we want to start running in a more privileged one. So this dropped, as a background, this drop file is another app native library, and we know that because its starting point is a function called JNI onload, which is a built-in aspect of Java native libraries. And so the exploit ends up using this app that's pre-installed on Samsung phones called Samsung Text-to-Speech to load and execute stage number 2. So the Samsung Text-to-Speech app is a system app running on all Samsung devices. It's pre-installed, part of the system image. And it is not quite as privileged as system server, but is still much more privileged than the untrusted app context we're running in. It's running as a system app. And so there were many versions of this application that would read a settings file of this application and then just load whatever native or whatever path was there in the settings. So the exploit took advantage of that because they had this first Clipboard vulnerability that allowed them to write and read to arbitrary files on the file system. So by changing that, they were able to get their stage 2 library past a system.load, which would load it and begin executing JNI unload. So what this looked like is actually pretty straightforward. They ended up using the Clipboard vulnerability to write it to 2 different settings files because the path was slightly different based on the device version. So the user DE, so many people have thought that meant it was targeting German users. It does not. DE stands for device encrypted. So just to clear that up off the bat. So it wrote to both of these files just in case instead of checking which version it was running on. And it just changed in the XML file this highlighted bit of what is your engine path, and it changed it to their stage 2. So now we're executing as a more privileged system app. And this is when they jump into the next 2 vulnerabilities. The first of one being kernel information leak. So what they're going to leak is the task struct address and a syscall table address. The task struct address will be used to access the adder limit member of the task struct, because the adder limit is important for the kernel's functioning and will be how they end up getting arbitrary kernel read and write. The syscall table address they use to break KASLR. And basically all they do for this info leak is abuse a warn on. Warn on macros are used in the Linux kernel to debug kernel failures. And because they're supposed to only be used for kernel failures, they include a whole lot of information in their logging when they're hit, including a full backtrace, which included stack contents. So this is the warn on that they were abusing in the exploit. This is a function within the Mali GPU driver. The Mali GPU is one of the generally 2 common GPU drivers that are used in the Android ecosystem. And so there was this warn on right here. So basically what this is an ioctl call. And if the ioctl is past an invalid command number, one that doesn't actually exist within the driver, then we hit the warn on. So this is all they had to do to trigger that, is they get a file descriptor handle to that specific ioctl driver, and then they pass in this invalid command, and now they've hit the warn on. After hitting warn on a few different times to make sure you got the good logs, they then turn on a bug report. So they end up calling these to set build properties for first a full bug report from dump state, and then they use CTL start to initiate the bug report. CTL.start property looks in the operating system's init to try and find a service and start. So this was a little funny because we're running in a system app context. At least on AOSP, the baseline open source version of Android, apps can't call CTL start because it is a basic sort of aspect of the initializing services within the operating system. So I ran SE search on the device to see, how is this able to do it? And lo and behold, there was a whole lot more access to the CTL start property than what I was expecting. And so including system app did in fact have permission to start and set the property, and that was how the exploit was able to initiate a bug report. So then I opened up dump state, which is the binary that this bug report service would call. Dump state is an aspect of AOSP, but it had been modified as a part of this Samsung device, specifically for this line right here at the beginning of the dump state function, which copied all of the contents from proc seclog to this file datalog seclog.log. Proc seclog is also a special customization for Samsung devices that have more sensitive security logs. And usually, apps would not be able to access contents like kmessage, which is where things like warn on are usually logged. But through proc seclog to datalog seclog, they did get access. And so specifically here, this was an example of the backtrace printed or logged whenever the warn on was hit. We have in this raw stack contents are task struct address as well as a syscall table address. And so the exploit had hard-coded knowing that it was looking for the values at B60 and BC0. So how did Samsung fix this? First, dump state no longer writes to seclog because the other thing was this seclog had very permissive SE Linux permissions so that apps could widely read it. They also removed this bug report service from dumpstate.rc because this service was a customization not found in OSP. But there also had been changes made in upstream components that would prevent this type of vulnerability in the future. So the first one had been in February 2020, ARM, who develops the Mali GPU driver, changed that warn on we were looking to a PR warn, which is a much more appropriate sort of function or macro to have there because it does not print a full backtrace. And secondly, in April 2020, Linux did remove printing the raw stack contents in backtraces for ARM64 because they realized like this is sensitive and doesn't have a huge amount of actionable info. Now we get to our priv-esc. So along with the other two, this was also patched in March 2021. So here we are. We're still running as our system app context, but we've leaked 2 pieces of information from the kernel. What now? So the vulnerability is a use after free of the file struct. And specifically, it is in Samsung's version of a driver for the display processing unit, which they called in an upstream commit DCON to stand for Display and Enhancement Controller, is the new IP in Exynos 7 SOC for generating video signals using pixel data. So that's what we're looking at. That's where this use after free exists. And so this use after free will be triggered again through an ioctl in the DCON driver. But first, the exploit needs a file descriptor to be able to call an ioctl on that driver, and that's not as straightforward as it would sound, because the full path for this driver can live in many different places. So what the exploit didn't know is that the path would include graphics/FB0 in the path, but that leaves a whole lot of different options. So instead, to figure it out, they made a 3-step approach. First, they wanted to find the PID of the process that's running that driver, or find a PID of a process that they knew would be running that driver. In this case, that's the graphics composer process, which is the hardware's abstraction layer on Android devices for the graphics. Then once they find that PID, they iterate through the process's file descriptor table and using readlink to find any of the full paths for each file descriptor that is open in that process. And then finally, they will use our vulnerability number 1 to open the FD again. So first, how do they find the PID? So they actually connected to LogReader, which is one of the basic sort of Android operating systems that sort of, controls Logcat in a way. So that's what it's similar to. And so they connect to a socket via there, say they want, a whole bunch of logs, including the system logs and the crash logs. And then they just wait and read and look for the term display. And when they find the term display at the beginning of a logging message, they then look at what PID was printed along with that term, and that's how they find the PID of the graphics composer process. So now we have a PID, which means we can iterate through proc PID FD table. And so they literally start at the beginning and open up each one, called readlink on it to see what the full path is, check if that full path contains graphic FB0. Once they found it, that was the path they would then use with vulnerability number 1 to open a file descriptor to that path, which is the DCON display driver. So the use after free was also a pretty common pattern that we have seen amongst kernel drivers before. So first, the driver acquires a file descriptor, an FD, for a fence. We don't really need to know all about fence internals, but the basics is that a fence is used in kernel drivers for sharing buffers and synchronizing access between different drivers or processes. So first, it's going to acquire that FD, And then it's going to associate that FD with a file struct. In this case, it's sync file and the file pointer member of that. Then the driver is going to call FD install. FD install makes a file descriptor accessible from user space. So before, we were just sort of all operating in the kernel. So now the driver has said, hey, user space, you can do operations on this FD now too. And when FD install is called, it transfers the ownership of the reference to the FD table. So in this case, if the driver had the only reference to the file struct that it's associating here and passes it to the FD table, and user, oh, I'm jumping ahead, and the user calls close, then that closes the only reference, or closes the only reference on that file struct, and the file struct is freed. But the driver does not realize that and assume that that file struct is still accessible and legitimate and will continue to access it, and that's how we got our use after free. So specifically in this case, looking at the code from the driver, we have this function, decon set when configured, which is accessible via an ioctl. So the first thing it does in this highlighted portion is it calls decon create fence, which is going to acquire that file descriptor for us and assign it to retire fence. So I know it might not sound like it if you haven't, but retire fence is actually the file descriptor. Then we're going to call FD install. So we're saying, hey, you can associate retire fence FD with this file pointer in the sync file struct. And then we call decon create release fences with that same sync file. And decon create release fences will acquire its own FD and assign that to rel fence. And then it calls FD install. This time, though, they do take an additional reference out using that get file, but they're using that same file pointer again, the one that was just freed by user space. So at the end of decon set when config, we have two FDs, retire fence, which is the closed FD that pointed to our freed file struct, and rel fence, which is an open FD with an additional reference taken on it, but still to our freed file struct. So that's our use after free. So the exploit strategy of that use after free that was taken was that the exploit replaces the freed file struct with a newly controlled file struct, one that they fake and create and set different members of. They're going to set the private data member that's within that file struct to point to the adder limit. We're going to then use signal FD to modify the adder limit, and that's how it's going to gain arbitrary kernel read and write. So that's the overview of what we're about to cover. Now I'm going to get into the details of what that means and what it looks like in this case. So to back up, what is the adder limit? It's the address limit. As I said before, it's a part of that member of the task struct, and it sets what is user space, or user space is able to write to any address below the adder limit. So when we're in user space, that's usually user DS, which is set to 7 FFFFF for ARM64. And then for kernel, it's set to -1 here being, the highest value. So the kernel should have access across the board. Signal FD, which we're going to use to write that adder limit, is a syscall that usually is for creating a file descriptor if you want to monitor and accept different signals that are being sent to your process. But the key here is that we're not actually going to open it on and ask it to open a new file descriptor. We're going to call this on one of these fake ones that we create. And when that happens, it only updates the 8-byte mask. Oh, yeah, see, I really emphasize that. So this is the signal FD function from this kernel. And the key point here first is that the syscall expects you to pass a mask of the signals you want to accept, but the kernel stores masks as the signals that should be blocked. So if you're, say, using this later on, just keep in mind that first It will mask out the sig kill and the sig stop bits, but then it's an inverse. So when we want to have -1 or FFFFFF written to the address limit, we will actually pass 0 into the signal FD because of this flipping. Then there is this branch where if you pass in a file descriptor of -1, you're telling it to open up a new file descriptor and create a signal FD file descriptor. But we're going to follow this else branch here. So first off, a part of this signal FD is it has this struct, signal FD context, CTX. CTX is a pointer to a signal FD context struct, which only has one member, which is the sig mask, which sigset T is also an unsigned long to keep in mind. So we're going to set that to our private data member of the file struct for the FD that is passed into the syscall. The man page says that whenever you use signal FD and you're going to specify your own file descriptor, that it must be an existing and valid signal FD file descriptor. The only check for that is checking if the FOP member of the file struct equals signal FD FOPS. So that is something we can get around with our fake struct. Lastly, this is where we do our write. So we're going to set the context sig mask into the now knotted mask that was passed into signal FD. But because we set context to the private data, this is equivalent to us saying file private data sig mask equals sig mask, which we will get to in a minute here of why that's interesting. So these are the different members set in the exploits fake file structs that they sprayed all over the heap to get their replacement. The first one wasn't really used. I think they were just using it for maybe identifying their own file structs. The second one is we're using the syscall table to calculate signal FD FOPS so that we can pass that check we just talked about. Then they use 7F as a reference count, and that's basically being used to identify when they have successfully replaced the freed object. Unfortunately, there was not enough time to get into this, but there will be a blog post published later this week if you're interested in the internals of the heap spray and how they do the replacement. And then finally, they set private data to adder limit pointer. Oh, okay, I forgot. So, since now private data equals the adder limit pointer, that means that when signal FD updates the sig mask, we're actually overwriting the adder limit. So we have this pretty strong primitive now, or the exploit does, of a repeatable, stable write to the address limit. But not so fast, it's not done. We can't just say, great, we have arbitrary kernel read and write done. Because there have been 2 mitigations added to ARM CPUs, and most modern Android devices now use the ARM v8 CPUs, which include these exploit mitigations called user access override and privilege access never, UAO and PAN. So PAN protects against the kernel directly accessing user space memory, whereas user access override works with PAN by allowing unprivileged load and store instructions to act as privileged load and store instructions when the UAO bit is set. We'll talk about what this looks like in practice now. So this is an example kernel write function that myself and Jan Horn used in an Android exploit from 2019. And so the way that before UAO and PAN that you could do this arbitrary kernel read and write is you open up a pair of pipes. To do a kernel write, for example, you would write the address of the buffer of the contents you wanted written into the kernel to one end of it, and you would read it into the kernel address that you wanted to write to on the other end. So the reason why this no longer works is first, if PAN is enabled because adder limit is set to kernel DS, then we cannot do this write because its buff is in user space memory. And privileged access never prevents the direct access to user space memory. But let's say we set kernel DS to something else so PAN wouldn't be on. that's when UAO comes into play. UAO will not be set if kernel DS doesn't equal, or if the adder limit does not equal kernel DS. So then this call will fail because we're trying to access kernel memory with unprivileged load and store instructions. So this is what the exploit did. Basically, they just switched the adder limit back and forth between user DS and kernel DS. So I don't really call this a bypass because they're just working within the way UAO and PAN are supposed to work. So walking through this, first we have two writes to one end of the buffer. It's the buffer we want to write into the kernel, as well as a pointer to the user DS value. Then it calls this function set adder limit to kernel DS, which sends a signal to another process in the exploit to do the whole signal FD process to send the adder limit to kernel DS. It then does a little bit of a sleep in there to wait to make sure that that set occurs, and then it can move on to the reads. So now that we're in kernel DS, it will read the contents from the other end of the pipe into the kernel address, and now it's done its kernel write. And so it will then set everything back to user DS so that it always enters these functions as user DS, reading back that pointer. So I think this is especially really interesting just because, yeah, they didn't need a bypass for UAO or PAN because the primitive was so strong for the adder limit that it just sort of works exactly with UAO and PAN, toggling that adder limit back and forth. They didn't have to use setFS, which is usually the function that folks will use to change the adder limit. But setFS includes mitigations of like making sure that that adder limit is set back to a user space address when returning to user space and things like that. So the primitive that they got really is what enabled them to get around UAO and PAN without really having to bypass anything. Post-exploitation. So they've gotten their arbitrary kernel read and write. What do they do to root? Honestly, it's pretty boring. They follow exactly what we've seen many, many Android exploits do for years, is they overwrite the current process's cred struct to get root privileges, and then they overwrite the current SE Linux context to vol D, where vol D is the volume daemon. And while it is a user space process, even in Android's documentation of sort of security boundaries, they treat it as if it's kernel because it has a lot of access. Unfortunately, this sample did not include the final payload and implant, but based on it being attributed or believed to be associated with a commercial surveillance vendor, I'm guessing it would likely look like the surveillance spyware that we've been seeing over and over again. So final thoughts. First, I think as much as we can see and talk about and publish about these real-world examples of what attackers are doing is really important because it helps us know as defenders what is the best return on investment in terms of where we want to put resources. Is it different fuzzing? Are there attack surfaces that are being exploited that maybe we need to focus on more? Are there mitigations that are not holding up and need changes to them and things like that? So I think this is important in that way. And of those considerations of the real world attacker, to me, some of the most notable is the example of only targeting manufactured specific components. This is what we generally assumed was happening. This is what we've heard anecdotally, especially with the increase in fragmentation across the Android ecosystem. But it's always good to have that tangible example. And in this case, also seeing that 2 out of the 3 bugs are logic bugs. There's been so much focus on memory corruption, which I think is rightly so. Like, memory corruption is largely how all of the 0 days are happening right now. You know, I think it was like 67% last year. But it's important to remember that we can't just say, hey, write everything in memory-safe languages, and things are done from there. Lastly, remembering that Java components are a really good attack surface. But overall, A lot of times when people write about in the wild exploits in 0 days, they're like, most sophisticated ever, great attacker, like mind-boggling, amazing. But really, this exploit's pretty meh. It's using a lot of techniques that we've seen in public work before. None of the vulnerabilities were all that awesome. And that comes back to us as attackers, because attackers are having success with meh types of exploits. And so even if we readjust our mind to, oh, this was found in 0 day 2 years ago, still, even in that context, these techniques were in use long before that. And this also highlights to me another thing to keep in mind is transparency around these in the wild 0 days. And it is something I have been talking about many, many times over and over for the last few years of studying these, because knowing what 0 days are being actively exploited and knowing the exploit techniques are in use is how we can really then make decisions of what types of steps to take next. So for example, performing root cause analysis to figure out what bugs are the attackers going after. Performing variant analysis to see, are there additional bugs that the attackers likely know about that the vendor only fixed one of? Doing patch analysis to see if the patches are actually sufficient. What types of detection techniques should we invest in that may actually work? Because detecting 0 days is hard when you're trying to detect something you don't know what it looks like. Lastly, it's not the end of the game when you patch a vulnerability. A vulnerability is only useful if you can exploit it. So looking at exploit techniques, how could you block that and make sure they have to come up with a new one instead of being able to plug and play with a new vulnerability and other hardening and systemic improvements. And so all of that, oh, I think I lost one. Oh, I meant to say it somewhere else. Oh, it was in the meh section. We can go back to meh. One thing that was interesting about this exploit as well, and especially focusing on the Java components, is that they probably could have written this exploit to only have to depend on that first clipboard bug. That had system server arbitrary file system access. And so maybe they didn't because they had this other infrastructure expecting kernel read and write or something for the payload. But that really highlights to me how it may be very worthwhile to do more looking at these custom components and things like system server, even when they're Java and you're thinking there's not going to be memory corruption. Because, yeah, there's probably there probably could have been some pretty interesting ways to just leverage that single vulnerability to meet their goal. And yeah, so my goal is always to try and learn from these 0 days, and I'm always happy to chat and talk about 0 days on and on and on. So I'm at Maddie Stone at Twitter, or we have this email address for things, and I keep a public tracking spreadsheet of 0 days in the wild, as well as we have a public repository of root cause analyses that we're trying to cover all the in the wild 0 days. But there tend to be a lot more than there used to be when I started that goal of covering them all. So yeah, we also accept pull requests. And that's it. Thank you. Any questions?
Muchas gracias, Maddie, por tu presentación. Comentarles que Maddie va a estar dentro del auditorio para poder responder sus dudas, preguntas o dificultades, así que por favor no se vayan del auditorio. Y también a continuación vamos a tener nuestra próxima charla, que la va a dar Juan Andrés Guerrero Sade.
Question. Yes.
Oh, okay.
No? See? So, from what you described, it seems that this exploit, or the chain of exploits, or the overall program, it's quite reliable, meaning it works all the time. So, it's 100% reliability. It doesn't depend on, well, there's a user after free, maybe, but it doesn't. The mitigations, the kernel mitigations, do not seem to have made any dent on it. Do you have any reliability considerations or numbers or metrics about this?
So the question is, are there
Do you think, or have you measured if this exploit worked all the time, 100% each time you run it?
I do not have metrics. I do believe it would be pretty reliable because each of the pieces of it, as long as it's the right versions of the device, were pretty reliable vulnerabilities in and of itself. The clipboard write is going to work every single time. The loading the exploit, which wasn't a vulnerability, but loading it via Samsung app, that's straightforward. The kernel leak might be the one place where you have to do it a few times, but there's not really then an issue with running it a few different times because it's not like you're going to crash the device from that. And then it seems like the use after free was pretty stable as well.
Thank you.
Hi, congratulations for a fantastic talk. It's really an honor to have someone from Project Zero here at Ekoparty, so please keep coming. My question is, you just basically burned a full exploit chain from a surveillance vendor, which is fantastic. But what are your thoughts about doing the exact same thing, maybe for the US government?
I do not know. When we see exploit samples, you don't know. If there are bugs in something and they're being exploited, I'm going to get them fixed.
Thank you.
Thank y'all.